curving of space-time that creates what we feel as gravity. A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now if the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light. And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. Its warps and curves in the fabric of space and time. Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
People followed his work, and they were anticipating, because of this wonderful thing he had done with general relativity, this recasting the laws of gravity out of his head, there was the thought he could do it again, and people want to be in on that.
Despite all that he had achieved, Einstein wasn't satisfied. He immediately set his sights on an even grander goal, the unification of his new picture of gravity with the only other force known at the time, electromagnetism. Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a magnet thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related. When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this on a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism in a single force called electromagnetism. And like Isaac Newton before him, Maxwell's unification took science a step closer to cracking the code of the universe.
That was really the remarkable thing, that these different phenomena were really connected in this way. And it's another example of diverse phenomena coming from a single underlying building block or a single underlying principle.
Imagine that everything that you can think of which has to do with electricity and magnetism can all be written in 4 very simple equations. Isn't that incredible? Isn't that amazing? I call that elegant.
Einstein thought that this was one of the triumphant moments of all of physics and admired Maxwell hugely for what he had done.
About 50 years after Maxwell unified electricity and magnetism, Einstein was confident that if he could unify his new theory of gravity with Maxwell's electromagnetism, he'd be able to formulate a master equation that could describe everything, the entire universe.
Einstein clearly believes that the universe has an overall grand and beautiful pattern to the way that it works. And so to answer the question, why was he looking for the unification? I think the answer is simply that Einstein is one of those physicists who really wants to know the mind of God, which means the entire picture.
Today, this is the goal of string theory: to unify our understanding of everything, from the birth of the universe to the majestic swirl of galaxies, in just one set of principles, one master equation. Newton had unified the heavens and the earth in the theory of gravity. Maxwell had unified electricity and magnetism. Einstein reasoned all that remained to build a theory of everything, a single theory that could encompass all the laws of the universe, was to merge his new picture of gravity with electromagnetism.
He certainly had motivation. Probably one of them might have been aesthetics or this quest to simplify. Another one might have been just the physical fact that it seems like the speed of gravity is equal to the speed of light. So if they both go at the same speed, then maybe that's an indication of some underlying symmetry.
But as Einstein began trying to unite gravity and electromagnetism, he would find that the difference in strength between these two forces would outweigh their similarities. Let me show you what I mean. We tend to think that gravity is a powerful force. After all, it's the force that right now is anchoring me to this ledge. But compared to electromagnetism, it's actually terribly feeble. In fact, there's a simple little test to show this. Imagine that I was to leap from this rather tall building. Actually, let's not just imagine it. Let's do it. You'll see what I mean. Now, of course, I really should have been flattened, but the important question is, what kept me from crashing through the sidewalk and hurtling right down to the center of the earth? Well, strange as it sounds, the answer is electromagnetism. Everything we can see, from you and me to the sidewalk, is made of tiny bits of matter called atoms. And the outer shell of every atom contains a negative electrical charge. So when my atoms collide with the atoms in the cement, these electrical charges repel each other with such strength that just a little piece of sidewalk can resist the entire Earth's gravity and stop me from falling. In fact, the electromagnetic force is billions and billions of times stronger than gravity.
That seems a little strange because gravity keeps our feet to the ground, it keeps the Earth going around the sun. But in actual fact, it manages to do that only because it acts on huge, enormous conglomerates of matter. You know, you, me, the Earth, the sun. But really at the level of individual atoms, gravity is a really incredibly feeble, tiny force.